March 19, 1945. The location is roughly 50 to 70 miles off southern Japan near Shikoku. The USS Franklin is operating in the most dangerous condition known to naval engineering. She is not merely a warship in this moment. She is a floating fuel refinery and a high-explosive depot operating under a single, unforgiving constraint. That constraint is the density of potential energy on her decks. The carrier is launching a strike against the Japanese mainland. Her flight deck is packed with Corsair fighters and Helldiver bombers. Every aircraft is fueled to capacity. Every hardpoint is loaded with ordnance. Below, on the hangar deck, the picture is just as crowded but not identical. Aircraft are packed tight, many of them gassed up and ready to be brought topside. Yet not every plane below is carrying a full bomb load. The danger is still extreme because heat and fire do not care what is officially armed. Rockets and bombs are already staged for the next wave, especially topside. In this condition, the safety margins are gone. Combat has stacked fuel and ordnance into every spare inch of steel. At 7:08 in the morning, the constraint snaps. A single enemy aircraft drops out of the low cloud cover. It achieves a perfect surprise. Before the heavy anti-aircraft guns can track the target, the attacker releases 2 bombs, each roughly 250 kilograms. Evidence suggests at least one of them is a semi-armor-piercing type. The physics of this attack should be survivable. 2 bombs of this size by themselves should not sink an Essex-class carrier. But the bombs do not strike the hull. They strike the loaded decks. The first bomb penetrates the flight deck and detonates amongst the fueled aircraft in the hangar. The second bomb drives into the ship near the after elevator, exploding around gallery deck level spaces. The initial blast wave is violent, but it is the secondary effect that dooms the ship. The explosions immediately ignite aviation fuel and the gas tanks of the parked aircraft. This creates a thermal event that triggers a phenomenon known as a cookoff. A cookoff is distinct from a standard detonation. In a normal sequence, a weapon explodes only when its fuse is triggered by impact or timing. A cookoff occurs when the ambient heat surrounding the weapon becomes so intense that the physics of the explosive material changes. The propellant inside a rocket or the high explosive inside a bomb absorbs the thermal energy until it destabilizes. It does not wait for a command. It self-initiates. On the Franklin, the cookoff begins instantly. The hangar deck transforms into a chaotic artillery duel fought inside the ship's own frame. The primary threat comes from the tiny TIM rockets. These are massive air-to-ground weapons, nearly 12 inches in diameter, designed to break hardened targets. As the fires rage, heat can set off rocket motors and cook explosives. Some rockets may lurch, skid, or even fire, turning the hangar into a pinball machine of steel and flame. Every violent movement and every blast spreads more fuel and more fire, which in turn cooks off more ordnance. General-purpose bombs begin to detonate from the heat, adding concussive overpressure to the shrapnel. The fire suppression systems are overwhelmed. Firemain pressure collapses across most of the ship, and hose teams are suddenly fighting a blaze with a strangled water supply. By mid-morning, the Franklin is dead in the water. She has lost propulsion. She has lost communications. The smoke is so thick it blots out the sun for ships miles away. The carrier begins to drift in the current, close to a hostile shore, while consuming herself from the inside out. The crew is no longer fighting the enemy aircraft. They are fighting the physics of their own payload. The survival of the ship now depends on a single grim question. Can the structural steel of the hull outlast the thermal output of the burning air group? Or will the heat soften the ship's strength, buckle her structure, and drive her down toward the sea before the fuel runs out? The greatest enemy of the Franklin is now her own design. The structural logic of a warship is defined by a single principle known as watertight integrity. To remain afloat after a hull breach, an Essex-class carrier is divided into hundreds of individual steel compartments. Each space is fitted with heavy doors and hatches that can be sealed airtight to prevent the ocean from flooding the ship. This geometry is designed to save lives during a torpedo attack or a collision at sea. But on the 19th of March, this same geometry turns the Franklin into a pressurized bomb. The blast waves from the exploding aircraft cannot escape. The heavy steel bulkheads and the armored flight deck contain the overpressure. Unlike some British carriers, the Franklin's flight deck is not an armored lid. The real armor sits lower. The hangar deck carries a heavy layer of special treatment steel on the order of 2.5 inches in critical areas. In this scenario, that strength becomes a brutal advantage and a brutal trap. Blast and pressure are forced to ricochet through enclosed spaces instead of venting cleanly. The shock rebounds off bulkheads and overheads, multiplying damage inside the ship until frames tear, plating buckles, and compartments fail. That containment sets up another killer mechanism, sympathetic detonation. A cookoff is heat doing the work. Sympathetic detonation is shock. One blast slams through the ship like a hammer, and if another weapon sits close enough, the percussive wave can trigger its explosive filler even without a functioning fuse. In those enclosed spaces, pressure can bypass what timing and impact were supposed to control. On the hangar deck, the tiny TIM rockets are racked in close proximity. They are heavy, close-racked weapons carrying a brutal warhead. Under heat and shock, ordnance can begin to go in ugly, cascading bursts. One violent detonation can set off another nearby, not as a neat line, but as a stuttering chain of concussions that no human can outrun. The effect is catastrophic. The blasts do not just burn, they rip bulkheads, tear ventilation trunks, and twist steel into shapes it was never meant to take. The damage moves vertically. Explosions and fire wreck the uptake and air intake paths that feed the boilers, and firefighting water can pour down through those same passages. In places, blast pressure drives smoke and flame back through the ducts in sudden, violent flarebacks. Below decks, engineering spaces become isolated pockets of heat, darkness, and choking air. The men below are separated from the men above by a layer of inferno that is physically impassable. The ship effectively breaks into two separate worlds, the burning surface and the suffocating depths. To fight this inferno, the surviving crew on the flight deck and the escort ships maneuvering alongside begin to pump water onto the carrier. They direct massive streams of salt water into the burning hangar to cool the ordnance. This introduces a new variable. The water extinguishes the fire, but it does not leave the ship. With the lower hull still tight, that firefighting water has nowhere to go. It collects high and to starboard, held in place by intact bulkheads. The weight of the water is immense. Hundreds of tons of liquid are now resting high in the ship's structure, far above the center of gravity. The carrier is trading one lethal physics problem for another. The explosions are destroying her internal organs, but the cure is slowly destroying her balance. The ship remains upright for now, but the margin of stability is eroding with every minute the hoses remain active. The Franklin is no longer just burning, she is becoming top-heavy, and the ocean is waiting for the center of gravity to shift just a few inches too far. About 300 men are trapped in a mess hall on the third deck. They are alive, but they are effectively buried. Above them, the hangar deck is a furnace of exploding ordnance. Below them, the engineering spaces are sealing up to prevent the spread of fire. The ventilation has failed. The lights have failed. In a steam-powered warship, that condition is a cascading failure. When the main steam lines are severed or the boilers are shut down to prevent explosion, the turbogenerators spin down. When the generators stop, the electrical grid collapses. The forced draft blowers that push air into the ship stop spinning. The fire pumps lose pressure. The ship becomes a dark, airtight tomb. The temperature in the mess hall is rising rapidly. The air is filling with smoke from the fires above. Panic is the natural reaction, but panic consumes oxygen, and the oxygen supply is finite. The standard escape routes are the armored trunks that lead up to the hangar deck. These are now impassable. They are either filled with fire or blocked by debris from the flight deck collapse. The men are sealed in a steel box with no apparent exit. One officer, Lieutenant Donald Gary, realizes that the geometry of the ship offers one remaining vertical path. He does not look for a door. He looks for the exhaust system. He finds the access hatch to the boiler uptakes. The uptakes are the massive steel lungs of the ship. They are the enclosed channels that carry hot exhaust gases from the boilers up through the ship's structure to the funnel. They are designed to handle extreme heat, but they are not designed for human transit. They are double-walled to prevent the exhaust temperature from roasting the surrounding compartments. Inside these walls, there is a narrow maintenance void. It is a vertical labyrinth of steel grating and ladders choked with soot and residual heat. It bypasses the hangar deck entirely, routing directly to the island structure on the flight deck level. Lieutenant Gary enters the uptake alone. The space is pitch black and the air is thin. He climbs upward, testing the temperature and the oxygen levels. He confirms the route is viable, then climbs back down to the mess hall. He organizes the 300 men into a single file line. This is not a disorderly sprint. It is a slow, blind crawl through the ship's respiratory system. The men must move by touch, feeling for the rungs of the ladders in the darkness. They move upward, deck by deck, inside the funnel structure, physically passing through the center of the fire without being consumed by it. They emerge on the flight deck island, gasping for fresh air. In a civilian disaster, this would be the end of the story. The survivors would evacuate. But on a warship still within enemy reach, survival is only the first step. The ship is still drifting. The boilers are still offline. The only way to save the vessel from running aground or being finished off by enemy aircraft is to restart the propulsion plant. Lieutenant Gary does not evacuate the ship. He leads men back down into the heat to keep the ship alive. In the smoke and chaos, he helps direct firefighting, and he presses into the engineering spaces where the struggle becomes brutally simple. Raise steam, restore power, and make the hull move again. In one fire room, he helps drive the effort to get at least one boiler back on the line, buying the ship a heartbeat of propulsion when she needs it most. The fires on the flight deck are subsiding, but the ship is still carrying the water used to smother them, trapped by sealed decks and scuppers choked with debris. It sloshes and shifts as the hull rolls, turning the firefight's residue into a moving weight. Naval architects have a name for what comes next. The free surface effect is the most dangerous instability a ship can face. When a solid weight, like a tank or a plane, is secured to the deck, its center of gravity is fixed. It pushes down at a specific point. But when a liquid is only partially filling a compartment, its surface remains horizontal while the ship rolls. As the ship leans to the starboard side, the water flows to that side. This shifts the center of gravity of the liquid further to the right, which pulls the ship down even harder. It is a positive feedback loop. The more the ship lists, the more the water moves to the low side and the more the list increases. On the Franklin, the list has stabilized around 13 degrees to starboard, and at moments it threatens to creep higher. To a layman, 13 degrees might sound manageable. To a naval engineer, it is the edge of the abyss. A carrier is a top-heavy structure by design, with a massive island and flight deck sitting high above the waterline. If the list pushes past her remaining margin of stability, she will not sink by inches. She will snap roll, capsizing in seconds and sealing men inside the hull. She will turn upside down in a matter of seconds, trapping every surviving crew member inside the hull. The primary damage control pumps are offline or lack the power to eject this volume of water against the pressure of the ocean. The drainage systems are smashed. The crew cannot remove the weight. Therefore, they must make a counterintuitive decision. They cannot lighten the starboard side, so they must intentionally make the port side heavier. This technique is called counter-flooding. Counter-flooding is a calculated risk that requires absolute precision. The damage control parties must deliberately open the sea valves on the undamaged side of the ship, allowing the ocean to flood the empty void spaces on the port side. The goal is to create a balancing moment that forces the ship back to an even keel. The danger is obvious. By adding more water to a sinking ship, the engineers are destroying her reserve buoyancy. They are making the entire hull heavier and causing it to sit lower in the water. If they flood too much, the ship sinks directly to the bottom. If they flood too little, the list remains and the free surface effect takes over. Working in the dark, often with manual wrenches, the damage control teams begin the sequence. They open the sluice valves to the port voids. They listen to the rush of water entering the hull. It is a race between the incoming stabilizing weight and the existing destabilizing list. Slowly, the physics of the hull begins to respond. The 13-degree list halts. It does not vanish instantly, but it stops growing. The ship hangs in the water, heavy and sluggish, riding deep with a reduced freeboard. She is no longer fighting the fire or the enemy aircraft. She is fighting gravity. The list corrects just enough to prevent the snap roll, buying time for the propulsion teams to finish their work. The Franklin is now a heavy, wounded beast, surviving only because her internal geometry has been artificially rebalanced by the very element trying to sink her. The current keeps sliding her toward the enemy coast, slow and relentless. She is a sitting target for any submarine or bomber that sorties from Kyushu. The surviving air group has been destroyed on deck, and much of the ship's fighting power is degraded by smoke, damage, and unreliable electricity. To survive, the ship must move. She has two options. She can be towed by another vessel, or she can resurrect her own main engines. In the end, she attempts both simultaneously. The heavy cruiser USS Pittsburgh maneuvers alongside the burning carrier. This is a delicate operation. The ocean swell is pushing the two massive steel hulls together. If they collide, the cruiser could sustain structural damage that would force her to abandon the rescue. The Pittsburgh passes a heavy towing wire to the Franklin's forecastle. The crew on the bow of the carrier, working amidst the smoke and the wreckage of the flight deck, manages to shackle the wire to the starboard anchor chain. They pay out the chain, allowing its weight to create a crucial curve in the line. This curve is known in marine salvage as the towing catenary. It is the only thing that prevents the tow wire from snapping. When a ship the size of the Pittsburgh pulls a ship the size of a carrier, the dynamic loads are enormous. The ocean does not allow for a constant, steady pull. The waves cause the ships to surge and heave independently. If the wire were pulled into a straight, tight line, the shock of a single wave would exceed the tensile strength of the steel. The wire would part instantly, potentially whipping back and killing the deck crews. The catenary acts as a massive shock absorber. As the ships drift apart, the weight of the heavy chain lifts out of the water, absorbing the energy of the surge. As they drift together, the chain sinks back down. The wire never becomes fully taut. The Pittsburgh begins to pull, taking the strain. The catenary holds. The Franklin begins to move, turning her bow away from Japan. She is under tow, but she is barely making headway against the wind and the drag of her own flooded hull. Deep inside the ship, the second half of the equation is being solved. The engineering teams that escaped through the uptakes have returned to the fire rooms. The conditions are almost extraterrestrial. The compartments are filled with smoke and residual heat from the fires that raged just hours ago. The men are wearing rescue breathing apparatus, which are heavy, uncomfortable, and limit their vision. They are working by the light of hand lanterns. Their objective is to relight the boilers. This is not a simple switch. A naval boiler is a complex pressure vessel that requires precise airflow, fuel atomization, and water feed. If they introduce fuel into a hot boiler without proper airflow, the fuel will vaporize and detonate, blowing the bottom out of the ship. They must manually operate the forced draft blowers. They must bypass the damaged fuel oil service pumps. They effectively rebuild the propulsion logic of the ship in the dark. Slowly, the pressure gauges begin to climb. The steam moves from the boilers to the main turbines. The throttlemen open the valves. For the first time in hours, the vibration of the reduction gears runs through the keel. The propellers begin to turn. The USS Franklin casts off the tow line from the USS Pittsburgh. She is no longer a barge. She is a warship again. The engineers bring the ship up to 14 knots. It is not her flank speed, but it is enough. As more steam comes back online, they work her higher. The list is stabilized. The fires are isolated. The Franklin sets a course for the fleet anchorage at Ulithi, putting the enemy coast behind her wake. She has transitioned from a salvage site back to a navigating vessel, powered by the sheer stubbornness of the men turning the valves in the dark. The number is 807. It is one of the highest loss of life totals ever recorded on a United States warship that was not sunk in action. The Franklin is a statistical anomaly. She is a vessel that was technically destroyed by every metric of ordnance delivery, yet she refused to acknowledge the physics of sinking. The cost of that refusal was paid by the crew who remained at their stations in the engineering spaces while the decks above them turned into a blast furnace. The aftermath of the battle is not a moment of celebration. It is a long, slow exercise in endurance. The ship must travel thousands of miles to reach a repair facility capable of handling the damage. She steams from the combat zone to the forward base at Ulithi, then onward through major waypoints in the Pacific, and finally through the Panama Canal to the Brooklyn Navy Yard. This journey is technically impossible. The ship has suffered massive structural deformation. The main deck plating is buckled from the heat. The hangar bay is a cathedral of twisted steel, where the fire burned hot enough to melt the aluminum skins of the aircraft and fuse the landing gear to the deck. Yet the Franklin makes this voyage under her own power. No tow drags her across the ocean crossing. The propulsion plant, resurrected by the men who escaped the mess hall, keeps turning the shafts. The engineers maintain steam pressure and condenser vacuum, nursing wounded machinery across half the globe. It is a feat of seamanship that rivals the combat action itself. When the Franklin finally enters New York Harbor, the city falls silent. She is the most heavily damaged ship to ever enter the port under her own steam. The crowds on the pier do not cheer. They stare. The flight deck is punctured by gaping holes where the bombs penetrated. The starboard side is scorched black from the waterline to the island structure. She lists slightly, still carrying the stubborn imbalance left by emergency counter-flooding and the long fight to regain stability. She is a ghost ship, carrying the physical evidence of a disaster that should have sent her to the bottom. The legacy of the Franklin is written in the manuals of naval architecture. Her survival proves that a trained crew can save a ship even when the damage exceeds the theoretical limits of the design. It shows those choices only matter when a crew turns them into action, sealing spaces, rerouting water, and refusing to yield. The men who flooded the port voids and the officers who led the escape through the uptakes demonstrated that damage control is not a passive defense. It is an aggressive, offensive action against the physics of destruction. Japanese reports claim the Franklin had been sunk. They spoke with absolute certainty. By bringing the ship back to New York, the Navy proved that claim false. The salvage was not about returning a combat asset to the line. The Franklin would be repaired, but the war would end before she could return to the Pacific theater. The mission was not tactical, it was symbolic. The salvage defined the difference between a casualty and a loss. The ship was burned, gutted, and broken, but she remained sovereign territory. She arrived at the pier in Brooklyn not as a wreck, but as a commissioned unit of the United States Navy, still under command, still under power, and still afloat.